Imagine a muscle so strong, it can lift its own weight dozens of times a minute.
Right.
And it's so precise it can shape microscopic puffs of air into the word hello. But here's the thing. It has absolutely no bones to support it.
Not at all.
Yeah, if you were engineering a machine to do this, you'd probably demand rigid levers, hinges, steel support beams. But today, we are looking at an anatomical miracle that defies all of that rigid engineering.
It really does. It's arguably the most complex biomechanical region in the human body.
Absolutely. So you, the listener, are about to explore the human tongue and, well, the dynamic floor of the mouth that supports it.
Because we are shifting from the static, bony architecture of the skull, which we've discussed in previous deep dives, into an area defined entirely by motion.
Right, motion and fluid dynamics.
Exactly, and incredibly tight real estate.
Spot on. So if our previous deep dive into Chapter 14 of Haidt and Gardner's textbook of Head and Neck Anatomy was about the hidden corridors of the head, this exploration of Chapter 15 is about the living ground.
The living ground, I like that.
Yeah. We are mapping the submandibular region, but let's establish our mission right away. We aren't here to just recite a list of muscular origins and insertions.
No, that would be incredibly dry.
It's terribly dry. Our goal is to build a functional spatial mental model in your head. We want to understand how a sip of water or a simple thought transforms into the coordinated physical miracles of speaking and swallowing.
And to do that, we have to understand the boundaries of this living ground first. Geographically, we are situated in the anterior triangle of the neck.
Okay.
But functionally, this region is married to the head. It is essentially the anatomical bridge connecting your jaw to your throat.
Okay, let's unpack this. If I'm visualizing this bridge, where are the structural borders? I assume the jawbone is the ceiling.
Yes. The superior boundary, the rigid structure that everything hangs from, is the inferior border of the mandible, your jawline.
Right.
And the inferior boundary, so the floor of this specific regional box, is the hyoid bone.
The hyoid bone, that's the floating bone in the upper neck, right? The one that doesn't articulate with any other bones.
Precisely. It is suspended entirely by ligaments and muscles. So the submandibular region is everything sandwiched between the rigid arc of your jaw and that floating hyoid bone in your neck.
Got it. But within that space, there is an actual physical floor to the oral cavity itself. I mean, if I open my mouth and look under my tongue, I'm looking at a mucosal lining. But what is directly beneath that? What is holding the tongue up and preventing it from just falling down into the neck?
You are looking at the foundational structure of the region, the mylohyoid muscle.
The mylohyoid.
Yes, it forms the literal true floor of the mouth.
Oh, yeah.
Everything else we are going to discuss today either rests upon it, wraps around it, or pierces right through it.
Wow. When I look at the anatomical diagrams of the mylohyoid, it doesn't look like a typical bicep or a calf muscle. It's broad and it's very flat.
It is.
It honestly looks like a muscular hammock or a suspension bridge slung between the left and right halves of the jaw.
That hammock analogy is structurally perfect, actually. To build that bridge, the mylohyoid originates along something called the mylohyoid line on the mandible.
And where exactly is that?
Picture a ridge running along the inside surface of your lower jaw. It starts from the midline of your chin, the symphysis menti, and sweeps all the way back to the area opposite your last molar teeth.
So it's anchored continuously along the entire internal horseshoe of the jawbone.
Yes. From that broad, sweeping anchor point, the muscle fibers fan inward and downward toward the center of your neck.
Okay.
The anterior fibers, so the ones closer to your chin, meet in the middle. They interlock with the fibers from the opposite side at a fibrous seam called the median ruff.
Ah, like lacing your fingers together.
Exactly. But the posterior fibers, the ones furthest back near your molars, don't meet in the middle.
What do they do?
They continue downward and insert directly into the body of that floating hyoid bone. This configuration creates a complete, tight, muscular seal beneath the oral cavity.
But here is where the mechanics get really interesting. Because it's a hammock suspended between a movable jaw and a floating bone, the mylohyoid has a dual function, right? Depending on which bone is locked in place.
Yeah.
It's a matter of leverage, isn't it?
It is entirely about leverage. Let's say the muscles lower down your neck, tense up, and hold your hyoid bone completely still. The hyoid becomes the fixed anchor.
Okay, the hyoid is locked.
Right. If the mylohyoid muscle contracts now, it pulls the mandible downwards towards the hyoid. It depresses the jaw, which initiates the opening of your mouth.
Oh, I see. But we can reverse the physics. If I clench my teeth and lock my jaw...
Then the mandible becomes the fixed anchor.
Right.
Now, when the mylohyoid contracts, it pulls the hyoid bone upwards and forwards. And because the mylohyoid forms the entire floor of the mouth, as it contracts and tightens, the entire floor elevates.
It lifts the living ground.
Yes. It lifts the floor, which physically pushes the massive weight of the tongue up against the roof of the mouth.
What?
This upward crushing motion is the absolute critical first mechanical step of swallowing. You cannot initiate a swallow without that hammock violently pulling upward.
That is brilliant engineering. But a hammock that critical isn't just hanging there unsupported. It needs guy wires.
Indeed it does.
And that brings us to a muscle that honestly sounds like a mythical creature. The digastric muscle.
The digastric is an anatomical marvel. Truly, it's arguably one of the most uniquely designed muscles in the human body. As the name implies, a D meaning two, and gastric referring to bellies, it consists of two distinct muzzle bellies connected by a single tendon.
But they don't run in a straight line. They form this massive V shape under the jaw.
They do. The posterior belly originates way back on the mastoid notch of the temporal bone, which is just behind your ear.
Okay, behind the ear.
From there, it descends forwards and downwards toward the hyoid bone. Meanwhile, the anterior belly originates from the gastric fossa, a small depression on the inside of the lower border of your chin. And it descends backwards and downwards toward the exact same point on the hyoid bone.
So you have one muscle pulling from the back of the skull and one pulling from the chin, and they meet in the middle of the neck. But wait, they don't actually attach to the hyoid bone directly, do they?
No, and this is where the mechanical genius lies. The two bellies meet at an intermediate tendon,
Ooh.
and this tendon passes through a fibrous loop, a physical sling of connective tissue that anchors it to the body and the greater cornu of the hyoid bone.
It's a literal pulley system? The tendon slides through a loop on a floating bone.
It acts exactly like a pulley. If both bellies contract simultaneously, they yank that intermediate tendon upwards, elevating the hyoid bone.
Okay.
Or if the hyoid is fixed in place by lower neck muscles, contracting the anterior belly helps the mylohyoid rip the jaw open against resistance.
But what I found truly fascinating, what really blew my mind reading through the source material, is why this muscle has two bellies. It isn't just an architectural quirk.
Not at all.
It's an evolutionary fossil.
It is a beautiful testament to how human development dictates the final wiring of our anatomy. Even though the anterior and posterior bellies act together in a single coordinated mechanical system, they are embryologically completely different structures.
They evolved from different tissues.
Exactly.
Let's delve into that, because this explains so much about how our nerves are laid out.
Right. So in the developing embryo, our head and neck form from structures called pharyngeal arches.
Okay.
The anterior belly of the digastric develops from the first pharyngeal arch, which is the mandibular arch. The nerve that supplies this first arch is the trigeminal nerve, cranial nerve V.
The fifth nerve.
Yes, specifically its mandibular division V3. So the anterior belly is wired to the trigeminal nerve via a branch called the mylohyoid nerve.
Okay, so the front half of the pulley system is wired to cranial nerve V.
Correct, but the posterior belly develops from the second pharyngeal arch, the hyoid arch.
A completely different origin.
Exactly. And the master nerve of the second arch is the facial nerve, cranial nerve 7. Therefore, the posterior belly receives its motor innervation from a completely different source, a branch of the facial nerve that enters its deep surface.
So you have a single, continuous mechanical cord under the jaw. But because millions of years ago, the front part evolved from one gill arch and the back part evolved from another, they have separate, dedicated power lines coming from completely different parts of the brain.
That is staggering, isn't it?
It really is.
Anatomy is rarely cleanly logical from a top-down perspective. It is a messy, beautiful accumulation of evolutionary history. And to finish reinforcing this muscular floor, we have two smaller muscles acting as stabilizers, the stylohyoid and the geniohyoid.
The stylohyoid sounds like it's connected to that sharp, pen-like bone under the skull, the styloid process.
That's exactly right. It arises from the styloid process of the temporal bone and descends to the hyoid. But structurally, it does something extraordinary. As it reaches the hyoid bone, the stylohyoid muscle physically splits in two.
It splits.
Yes. It is perforated by the intermediate tendon of the digastric muscle we just discussed.
Wait, really? So the digastric tendon actually threads the needle right through the middle of the stylohyoid muscle to reach its pulley on the bone.
It threads the needle perfectly.
Wow.
This creates an incredibly tight integrated network of tension. The stylohyoid pulls the hyoid bone superiorly and posteriorly up and back. And because it travels with the posterior digastric, it shares the same embryological origin and is also wired to the facial nerve.
Okay. And the geniohyoid, where does that sit in this scaffolding?
The geniohyoid rests directly on top of the mylohyoid hammock, right in the midline.
Inside the mouth, essentially.
Exactly. It originates from the inferior mental spine of the mandible, just behind the chin, and runs straight back to the body of the hyoid bone. Its job is to pull the hyoid bone straight forwards.
All right, so let's lock in this mental model before we put any weight on it. We have the jawbone as the rim. We have the broad mylohyoid acting as the muscular hammock sealing the bottom. We have the geniohyoid sitting on top of the hammock pulling forwards. We have the digastric pulley system acting as the heavy-duty guy wires from the front and back, and the stylohyoid threaded onto those wires pulling up and back. The foundation is poured. The floor is built.
Which means we can finally discuss the massive, restless inhabitant that lives on top of this floor.
The tongue.
The tongue.
Now, I have to push back on something here. When I think of a muscle-generating complex movement like an arm swinging or fingers typing, I picture a muscle pulling on a rigid bone to create a lever.
Naturally.
But the tongue is a massive block of muscle with zero internal skeleton. How on earth does it not just contract into a useless, spasming knot? How does it create the unbelievably fine, precise movements required for articulating the letter S or positioning a single peanut between the molars?
That is the perfect question, and it gets to the heart of what the tongue actually is. The tongue is a muscular hydrostat.
A muscular hydrostat.
Yes. It operates on the same mechanical principles as an elephant's trunk or an octopus's tentacle.
Oh, wow.
Because muscle tissue is mostly water, it is incompressible. If you squeeze a water balloon in the middle, the ends have to bulge out. The tongue uses this exact fluid dynamic property to move.
So by contracting in one area, it forces the rest of the tissue to expand in another direction.
Exactly. And to orchestrate this, the musculature of the tongue is divided into two highly distinct functional categories. You have the intrinsic muscles and the extrinsic muscles. You can think of them as the shapeshifters versus the directors.
I like that. Let's look at the shapeshifters first, the intrinsic muscles.
The intrinsic muscles are entirely contained within the body of the tongue. They have no bony attachments whatsoever. Their sole job is to alter the physical shape of the tongue.
Okay.
The fibers run in three different dimensions. The longitudinal group runs front to back, the transverse group runs side to side, and the vertical group runs top to bottom.
So if the vertical fibers contract, squeezing the top and bottom together, the tongue flattens out.
Exactly.
And if the transverse fibers contract, squeezing the sides together, the tongue becomes long and narrow.
Precisely. You can curl the edges into a taco shape, shorten it into a thick lump, or elongate it into a point. But shaping the tongue is only half the equation. A narrow, pointed tongue is useless if you can't move that point to the front of your teeth.
Right.
That is where the directors come in, the extrinsic muscles.
The extrinsics, these are the muscles that originate from rigid bone outside the tongue and then dive into the meat of the tongue to move the whole structure around.
Correct. They originate from bony landmarks and intermingle heavily with the intrinsic fibers. There are 4 main extrinsic muscles, and 3 are fundamentally rooted in this submandibular region.
And the biggest one.
The most massive of these is the genioglossus.
Genioglossus. Genio meaning chin, glossus meaning tongue.
Right. The genioglossus originates from a single point on the inside of the chin, the superior mental spine. From that narrow anchor, this huge muscle fans out dramatically. Its fibers spread to enter the entire length of the inferior surface of the tongue, from the root all the way to the tip.
So it's shaped like a giant fan blade opening up inside the mouth. What happens when that fan fires?
When the bulk of the genioglossus contracts, it pulls the base of the tongue forwards. It is the primary muscle responsible for protruding the tongue, sticking it out of your mouth.
Okay.
The most anterior fibers also work to pull the tip of the tongue down.
So the genioglossus drives the tongue forwards and down. We need something to pull it backwards.
That would be the styloglossus.
Yeah.
Originating from the styloid process near the skull base, it descends forwards and inwards to enter the sides of the tongue.
Right.
When it contracts, it violently retracts the tongue, pulling it backwards and elevating the tip.
So we have a tug of war. Genioglossus pulls forwards. Styloglossus pulls backwards and up. What pulls the sides of the tongue down?
The primary depressor is the hyoglossus. This muscle originates from the hyoid bone and rises vertically, straight up to enter the side of the tongue.
And when that fires?
When the hyoglossus fires, it flattens the tongue by pulling its side straight down towards the neck.
Yeah. Okay. And there's a fourth one mentioned, the palatoglossus, right?
Yes, but the text notes it as a functional exception. The palatoglossus originates from the soft palate above and descends into the tongue. Structurally and neurologically, it is truly a muscle of the palate, acting to elevate the root of the tongue to seal the back of the throat.
So getting back to the octopus tentacle analogy, you don't just have one muscle firing at a time. It's a symphony.
A very complex one.
Yeah, the intrinsic vertical fibers might contract to flatten the tongue, while the extrinsic genioglossus pushes that flattened shape forwards, and the extrinsic styloglossus micro-adjusts the tension so it doesn't go too far.
It is a continuous, highly calculated flux of muscle tension. But a symphony of this complexity requires an absolute master conductor. All of these intersecting, overlapping fibers require incredibly precise wiring.
They really do.
And that brings us to the functional integration of this region, the neurology.
Right, because the wiring in the floor of the mouth seems completely chaotic at first glance. I mean, you have massive nerve bundles crisscrossing over each other, carrying completely different types of signals.
Motor commands, sensory data.
Raw pain data, delicate taste data, and autopilot commands for saliva. Let's isolate the motor command center first. How are all these tongue muscles getting their movement orders?
The motor control is surprisingly streamlined compared to the rest of the region. Almost the entire motor command of the tongue is governed by a single powerful nerve, the hypoglossal nerve, cranial nerve 12.
Hypoglossus, literally under the tongue.
Exactly. Cranial nerve 12 exits the skull, drops deep into the neck, and then sweeps forwards. It passes deep to the posterior digastric, crosses right over the major arteries, and runs parallel to the hyoid bone, straight along the side of the genioglossus muscle, all the way to the tip of the tongue.
And it controls everything.
It innervates all of the intrinsic muscles of the tongue and all of the extrinsic muscles of the tongue, with the single exception of that palatoglossus muscle we mentioned. For the mechanical movement of the tongue, cranial nerve 12 is the absolute authority.
But knowing that 12 is the sole authority makes it a single point of failure. The text outlines a specific clinical scenario involving the hypoglossal nerve that I want to bring in here because it perfectly illustrates the mechanical tug-of-war we just talked about.
Ah, you're referring to a hypoglossal nerve lesion.
Yes. Let's say I go to the dentist to have a difficult lower wisdom tooth extracted. The roots are deep, it's a traumatic extraction, and the surgeon accidentally stretches or severs the right hypoglossal nerve deep in the submandibular space.
Okay.
What physically happens to my tongue?
A unilateral lesion damage to only one side causes a profound mechanical imbalance. If your right hypoglossal nerve is severed, the muscles on the right half of your tongue instantly lose their motor command. They go entirely flaccid, paralyzed.
But the left side.
The muscles on the left half of your tongue, innervated by the perfectly healthy left hypoglossal nerve, maintain their full strength.
Okay, so I have half a paralyzed tongue. What does the clinician see when they ask me to stick my tongue out?
The clinical presentation is unmistakable. When the doctor asks you to protrude your tongue, your brain sends the command down both nerves. The right nerve is dead, so the right genioglossus does nothing.
Right.
But the left nerve fires perfectly. The massive left genioglossus contracts powerfully, pushing the left base of the tongue forwards.
So the left side pushes forwards forcefully, but the right side is just dead weight dragging behind.
Precisely.
Yeah.
I like to compare it to a rowboat with two oars.
Oh, that makes perfect sense.
If you are rowing a boat and you suddenly snap your right oar, but you keep pulling hard on your left oar, what happens to the boat?
The boat violently turns to the right. It turns towards the broken side.
Exactly. Because the healthy left genioglossus is pushing forwards and the right side offers no resistance, the entire body of the tongue deviates or points towards the paralyzed side. The tongue points directly at the lesion. It is a flawless mechanical indicator of a cranial nerve 12 deficit. And over time, those paralyzed muscles on the right side will physically atrophy and shrink, making that side of the tongue look severely wrinkled compared to the plump, healthy left side.
That is the beauty of applied anatomy. Pure physics diagnosing a severed nerve. All right, so cranial nerve 12 is the master motor conductor. But what about the sensory side?
Right.
If I bite my tongue or burn it on scalding tea or taste a piece of perfectly salted caramel, none of those signals are traveling on the hypoglossal nerve, right?
Not a single one. Sensation and taste belong to an entirely different, highly complex network that we can call the sensory and autonomic superhighway. And this involves two other major cranial nerves, the trigeminal nerve, cranial nerve V, and the facial nerve, cranial nerve 7th.
Let's untangle the trigeminal side first.
The mandibular division of the trigeminal nerve, known as V3, sends a massive branch down into this region called the lingual nerve.
And the lingual nerve's job is strictly feeling, touch, and pain.
Yes, general somatic afferent sensation. The lingual nerve is responsible for touch, pain, and temperature sensation for the anterior two-thirds of the tongue. It also provides sensation to the adjacent mucous membranes and the gums on the inside of your lower teeth.
So when I burn the front of my tongue on tea, the lingual nerve is the alarm bell firing that data back to the trigeminal system in the brain.
Correct. The lingual nerve drops down from the skull, courses obliquely across the submandibular region, passing right under the salivary ducts to spread its sensory receptors all over the front of the tongue.
But the text describes something extraordinary happening inside the lingual nerve. It isn't just carrying pain data, it's carrying data for a completely different sense, from a completely different cranial nerve.
This is the phenomenon of anatomical hitchhiking. As the lingual nerve descends towards the mouth, it is physically joined by a small, highly specialized branch of the facial nerve, cranial nerve to seventh. This branch is called the chorda tympani.
The chorda tympani, it sounds musical, but what is its function?
It carries two very specific, delicate sets of data. First, it carries special sensory fibers for taste, specifically taste for the anterior two-thirds of the tongue.
Wait, I need to make sure I understand this. The pain from a burn on the tip of my tongue travels to the trigeminal nerve, but the taste of the sugar on the exact same tip of my tongue travels to the facial nerve.
Yes. The taste buds on the anterior tongue transmit their electrical signals into the chorda tympani fibers. But the chorda tympani is a tiny, fragile nerve. Instead of navigating the treacherous muscular environment of the neck all the way back to the skull base on its own, it physically merges into the massive structural cable of the lingual nerve.
It's literally using the lingual nerve as a subway tunnel.
It is the ultimate biological efficiency. Think of the lingual nerve as a thick underground conduit for fiber optic cables.
Okay, I can picture that.
Inside that conduit, you have millions of fibers carrying raw touch and heat data upwards to the trigeminal headquarters. But bundled right next to them, using the exact same physical pipe, is a separate bundle of chorda tympani fibers carrying taste data upwards to the facial nerve headquarters.
That is incredible. But the chorda tympani is a two-way street, isn't it? It isn't just carrying taste data up to the brain. It is carrying action commands down from the brain.
Yes. The second set of fibers within the chorda tympani are preganglionic parasympathetic fibers. These are the autonomic, involuntary commands that tell your salivary glands to turn on and produce saliva.
The plumbing commands.
The secretomotor commands. These parasympathetic fibers travel downwards inside the lingual nerve until they reach a very specific relay station located in the submandibular region.
And where is that?
This relay station is suspended physically off the lingual nerve itself, resting right on the hyoglossus muscle. It is called the submandibular ganglion.
A ganglion is essentially a junction box, right? A place where nerve cables end and new nerve cables begin.
Exactly. It's a synaptic relay. The preganglionic fibers from the brain exit the lingual nerve conduit, enter this ganglion, and synapse, they chemically connect with the cell bodies of postganglionic fibers.
And once the signal jumps the gap in that junction box, where does the final command go?
The postganglionic fibers emerge from the ganglion. Some dive directly into the massive submandibular gland located right next door.
And the rest?
Others actually jump back onto the lingual nerve to continue their journey forwards, eventually peeling off to innervate the sublingual gland and the thousands of minor salivary glands scattered throughout the mucosal lining of the mouth.
So to recap this insane superhighway, the brain decides it wants saliva. The facial nerve fires a signal down the chorda tympani. The chorda tympani splices itself into the trigeminal's lingual nerve.
Right.
The signal rides the lingual nerve down into the neck, hops off the junction box, jumps the gap, and then either dives into a gland or gets back on the lingual nerve to travel further forwards.
It is a convoluted masterpiece of functional integration. And since we have traced the commands to turn on the plumbing, we must now discuss the physical plumbing itself. The salivary glands.
Right. Because this living ground we're discussing requires constant lubrication. Without saliva, we can't speak, we can't taste, and we certainly can't begin the chemical digestion of food.
No, you'd be miserable.
The text focuses on two of the three major pairs of salivary glands, the submandibular and the sublingual. Let's start with the big one, the submandibular gland.
The submandibular gland is substantial, roughly the size of a walnut. It occupies a large portion of the submandibular triangle we defined earlier. If you feel under your jawline about halfway back, you can often palpate the superficial portion of it.
Well, okay, I can feel it.
It sits just beneath the skin and the thin platysma muscle, extending downwards over the digastric muscle.
But it isn't just sitting on the outside of the neck. It penetrates into the floor of the mouth.
Yes. It has a C shape. The bulk of the gland sits outside, resting against the mylohyoid muscle.
Yeah.
But it has a deep, finger-like extension. The deep process that wraps right around the posterior free edge of the mylohyoid hammock, pushing its way into the actual oral cavity under the tongue.
It hooks over the back of the hammock.
Precisely. And it is from this deep process, now inside the oral cavity, that the primary hose of the gland emerges. This is the submandibular duct, traditionally known as Wharton's duct.
And where does Wharton's duct run? How does the saliva actually get into the mouth?
Wharton's duct travels anteriorly, forwards, running tightly between the myomyoid and the genioglossus muscles. It passes right alongside the sublingual gland until it reaches the very front of the mouth.
Yeah.
It finally opens into the oral cavity at a tiny raised papilla called the sublingual caruncle.
The sublingual caruncle. If you lift your tongue in the mirror, there is a tight band of tissue connecting the underside of the tongue to the floor, the lingual frenulum.
Right.
And right at the base of that band, there are two little bumps. Those are the caruncles.
Exactly. Sometimes, if you yawn widely, you might actually feel a fine jet of saliva shoot out from those tiny bumps. That is the submandibular gland firing its contents through Wharton's duct.
Ah, I've had that happen. Okay, what about the sublingual gland? The name implies it sits directly under the tongue.
It does. It is the smallest of the three major salivary glands, shaped somewhat like an almond. Unlike the submandibular gland, the sublingual gland is housed entirely within the floor of the mouth.
It doesn't wrap around the hammock.
No, it sits on top of the mylohyoid hammock, right beneath the mucosal lining. It is sandwiched between the genioglossus muscle medially and the inner surface of the jawbone laterally.
And does it have one big duct like Wharton's?
Its plumbing is more diffuse. The sublingual gland drains primarily through a series of 8 to 20 tiny excretory ducts called the ducts of Rivenus.
Ducts of Rivenus, okay.
These ducts open directly onto the elevated crest of mucous membrane above the gland, known as the sublingual fold. However, the text notes that some of the anterior ducts can merge to form a larger channel, Bartholin's duct, which actually taps directly into Wharton's duct to share a common exit at the caruncle.
The plumbing systems can merge. Now, while we're talking about this plumbing, the text introduces a vital diagnostic procedure used when this system fails. Scilography.
Yes. Because these ducts are narrow and travel against gravity, they're highly susceptible to obstruction. A patient may develop a scilolith, a calcified salivary stone, or a stricture, or a tumor that compresses the duct.
And if the autonomic nervous system is screaming at the gland to produce saliva, but the hose is blocked with a stone, the pressure buildup must be agonizing.
Oh, it is. It causes acute, severe swelling and pain beneath the jaw, particularly right before or during a meal when the secretory drive is highest. To diagnose the exact location of the blockage, a clinician uses scilography.
How does that work? You can't just x-ray saliva.
No, saliva is radiolucent. The clinician has to carefully insert a tiny tube into the opening of the duct at the sublingual caruncle. They then inject a radiopaque contrast medium backwards into the duct system.
Oh, backwards.
Yes. The fluid flows retrogradely, filling the entire ductal tree. A radiograph is then taken. The contrast fluid glows bright white on the X-ray, highlighting every branch of the plumbing. Wherever the white fluid suddenly stops or pools, that is the exact location of your obstruction.
It's like putting fluorescent dye into a river to find exactly where the beaver dam is located.
Exactly. It visualizes the invisible.
Okay, so we have built the muscular hammock. We have mounted the shape-shifting muscular hydrostat of the tongue. We have wired it with 5 different sets of nerve cables.
A lot of cables.
Yeah, and we have plumbed it with salivary glands. But none of this living tissue can survive, let alone operate at the metabolic rate required for constant speech and chewing, without a massive high-pressure supply of fuel.
And a highly efficient waste removal system. Which brings us to the vascular networks and the lymphatics.
This region must burn a staggering amount of energy. I mean, the tongue alone is in near constant motion. The arterial supply here must be massive. Where is the fuel coming from?
The primary fuel lines are derived from the external carotid artery, the massive pipeline ascending the neck to supply the face and scalp. The text highlights 2 major branches that service the submandibular region, the lingual artery and the facial artery.
Let's trace the lingual artery's expedition first.
The lingual artery usually branches off the external carotid near the greater cornu of the hyoid bone. From the moment it arises, it seeks deep protection.
Right.
It dives deep to the posterior digastric, deep to the stylohyoid, and crucially, it passes deep to the hyoglossus muscle.
It buries itself under the muscular floor for protection.
It does. It ascends into the base of the tongue and turns forwards, tunneling all the way to the tip. Along this journey, it gives off 4 major supply branches.
What's the first one?
First is the suprahyoid artery, which stays low to supply the muscles attached to the hyoid bone. Next is the dorsal lingual artery. This branch ascends to the back, the posterior dorsum, of the tongue, supplying the mucous membranes, the tonsils, and the soft palate.
Supplying the back half of the living ground?
Yes. Third is the sublingual artery. This one is critical. It arises at the anterior edge of the hyoglossus muscle and courses forwards right between the genioglossus and the mylohyoid.
And its target?
Its primary job is to vascularize the sublingual gland we just discussed, as well as the adjacent muscles and the mucosa of the floor of the mouth.
And the final branch?
The deep lingual artery. This is the terminal continuation of the main artery. It runs immediately beneath the mucous membrane on the underside of the tongue, traveling alongside the lingual nerve all the way to the tip.
Okay.
At the tip, it actually anastomoses. It physically connects and shares blood flow with the deep lingual artery from the opposite side of the tongue.
That anastomosis is a critical failsafe. If one artery gets compressed, the other side can push blood across the midline to keep the tissue alive. Redundancy.
The body never relies on a single supply line for critical architecture, and that redundancy extends to the second major artery, the facial artery.
Now, the path of the facial artery completely surprised me. It doesn't just go around the structures in the neck, it goes through them.
It does. The facial artery arises just slightly above the lingual artery. Initially, it ascends deep to the digastric pulley system. But to reach the face, it alters course and literally passes directly through the glandular substance of the submandibular gland.
It punches a tunnel straight through the salivary gland.
It does, giving off glandular branches to supply the submandibular gland from the inside out as it passes through. It then hooks over the lower border of the mandible to supply the face.
Oh.
But just before it crosses the jaw, it gives off a critical branch for our region, the submental artery.
The submental artery, where does that go?
It courses forwards, right along the inferior surface of the mylohyoid hammock, supplying it, and the anterior digastric. But here is the critical failsafe. The submental artery sends a deep branch that actually punches through the mylohyoid muscle to enter the floor of the mouth, where it anastomoses with the sublingual artery.
So the lingual artery system, which comes from the inside, and the facial artery system, which comes from the outside, literally crosstalk through the muscular floor to share blood.
Yes. But this exact redundancy, this beautiful anatomical safety net, can become a surgeon's worst nightmare.
Right.
The text outlines a specific clinical scenario involving the sublingual artery that is absolutely terrifying if you don't understand the spatial variance.
Let's weave that in right now, because the stakes here are life and death. The text warns about dental surgeons operating in the anterior floor of the mouth.
Right. Say a dental surgeon is placing an implant in the lower front jaw. The drill slips, or the incision goes too deep, and they sever a major vessel in the floor of the mouth. It's a profound hemorrhage. Based on textbook anatomy, what artery is bleeding?
The sublingual artery, which branches off the lingual artery?
Correct. The standard surgical response to a massive hemorrhage that you cannot clamp locally is to ligate or tie off the source vessel further upstream. If the surgeon assumes standard textbook anatomy, they will urgently dissect the neck and tie off the main lingual artery, expecting the bleeding in the mouth to stop.
Because they shut off the main water valve.
Right. But human anatomy is highly variable. In a significant percentage of patients, the sublingual artery does not arise from the lingual artery at all.
Wait, what?
Instead of branching off the lingual artery, the sublingual artery arises entirely from that submental branch of the facial artery, the one that perforates up through the mylohyoid muscle from below.
Oh, no.
Exactly.
No.
If the patient has this anatomical variant and the surgeon ties off the lingual artery, well, nothing happens. The severed sublingual artery in the mouth continues to pump high-pressure arterial blood unchecked because its actual fuel line is coming from the facial artery system below the floor. The surgeon is desperately tying off the wrong pipe while the patient bleeds out.
That is horrifying. It vividly proves the point of this entire deep dive. Rote memorization of a textbook diagram is not enough. You have to understand the three-dimensional space, the fail-safes, and the predictable variance. Anatomy dictates the surgical strategy.
It is the absolute core of clinical reasoning.
Okay, so that is the high-pressure fuel coming in. What about the drainage, the waste removal?
Venous drainage generally mirrors the arterial supply. But clinically, the most visible vessel is the deep lingual vein.
The one under the tongue.
Yes. If you look at the ventral surface of your tongue, the underside in a mirror, you will see a large, dark blue, tortuous vein running prominently on either side of the midline. That is the deep lingual vein,
It is incredibly superficial. The mucosa over it is practically translucent.
which makes it a brilliant clinical pathway for drug delivery. Because the mucosa is so thin and the vein is so large and superficial, medications like nitroglycerin for angina can be placed under the tongue sublingually.
Right.
The drug diffuses right through the mucosa directly into the deep lingual vein, entering the systemic bloodstream almost instantly, completely bypassing the harsh acids of the stomach and the first-pass metabolism of the liver.
A built-in intravenous line under the tongue. But while the veins handle the blood, there is a third, parallel plumbing system in this region that the text treats with absolute gravity. The lymphatic system, the immune security and waste drainage network.
We cannot overstate the importance of the lymphatics here. The submandibular and sublingual regions have a massive, highly structured lymphatic drainage pattern. And understanding this pattern is not anatomical trivia. It is the sole factor that dictates life, death, and the extent of surgical disfigurement when we discuss cancer.
The text details several node groups, the submental nodes under the chin and the submandibular nodes located right alongside the submandibular salivary gland.
Yes, these nodes act as the primary filter traps. They drain a wide area: the lips, the gums, the floor of the mouth, and specific parts of the tongue. The efferent vessels, the output channels from these nodes, then drain downwards into a massive chain of nodes deep in the neck, called the deep cervical lymph nodes.
But the text zeroes in on one specific deep cervical node with terrifying emphasis, the jugulogastric lymph node.
The text explicitly labels it the principal node of the tongue. It is a massive lymph node located precisely where the posterior belly of the digastric muscle crosses the internal jugular vein in the neck. A vast amount of lymphatic fluid from the tongue drains directly toward this specific node.
Why is that particular node sitting on that particular vein so critical to understand?
To understand that, we have to transition into the darkest clinical correlation of the text: lingual cancer. Cancer of the tongue is the most common malignancy of the oral cavity, making up over 36% of all oral cancers.
And what kind of cancer are we talking about?
Over 95% of malignancies on the tongue and the floor of the mouth are squamous cell carcinomas cancers of the mucosal lining itself. And they are heavily statistically correlated with the combined use of high levels of alcohol and tobacco, which acts synergistically to mutate the mucosal cells.
The text maps out where these tumors usually appear. 2/3 occur on the lateral surfaces, the sides of the middle third of the tongue.
Right.
The rest generally appear on the underside or the front. But here is where the lymphatic map becomes horrifyingly relevant. The text makes a massive distinction in survival rates based on whether the tumor is on the front of the tongue versus the back of the tongue.
This is where anatomy dictates pathology. The lymphatic drainage of the tongue is not uniform. If a patient develops a squamous cell carcinoma on the anterior portion of the tongue, the front, the cancer cells must travel through a multi-stage sequential lymphatic pathway.
Okay, what does that path look like?
They drain first to the submental or submandibular nodes, and only later, as the disease progresses, do they finally reach the deep cervical nodes in the neck.
So a tumor on the front of the tongue has a long obstacle-filled runway before it can spread systemically.
Precisely. It gives the clinician time to identify the lesion, biopsy it, and perform a localized excision before it spreads to the rest of the body. But malignancies that occur in the posterior portion of the tongue, the back, are a completely different beast.
Because of the plumbing.
Because of the plumbing. The lymphatic vessels from the posterior tongue bypass the superficial nodes entirely. They drain almost directly into the deep cervical lymph nodes, specifically targeting that jugulogastric node we just highlighted.
And the jugulogastric node sits directly on top of the internal jugular vein.
The largest vein in the neck. Once a cancer cell reaches those deep cervical nodes, it has practically breached the fortress wall. It has immediate fast-track access into the systemic venous bloodstream to travel to the lungs, the brain, the bones. Posterior tongue cancers metastasize aggressively and incredibly early.
A small, painless ulcer on the back of the tongue could already be silently seeding the deep nodes, while a larger, uglier tumor on the tip of the tongue is still entirely localized.
Exactly. This is why a posterior lesion often requires an immediate, massive surgical intervention. A radical neck dissection, stripping out the muscles, veins, and lymph nodes of the neck to chase the microscopic spread. The exact location on the living ground dictates the grim reality of the surgical outcome.
It's a sobering reminder that this brilliant functional architecture is also highly vulnerable. Which brings us, finally, to the integration of everything we've discussed today.
Bringing it all together.
Yeah. We have spent over an hour dissecting this region piece by piece. We laid the mylohyoid hammock, we rigged the digastric pulley, we mounted the shape-shifting hydrostat of the tongue, we wired the motor and sensory superhighways.
And plumbed the glands.
Right. We turned on the salivary plumbing, fueled it with the lingual and facial arteries, and mapped the lymphatic security system. Now we need to see it work as a unified machine. Let's look at the act of swallowing, or deglutition.
Swallowing is perhaps the most perfectly timed, intricately coordinated biomechanical sequence that we perform mindlessly hundreds of times a day. It requires every single system we just mapped to fire in absolute harmony. Let's trace a single bite of food through the submandibular region in slow motion.
Okay, I've chewed my food. The saliva from the submandibular and sublingual glands, triggered by the facial nerve hitchhiking on the lingual nerve, has turned the food into a soft, lubricated ball called a bolus. What happens first?
The sequence begins with the intrinsic shapeshifters of the tongue. The superior longitudinal and transverse intrinsic muscles contract. They physically alter the shape of the tongue, curling the sides up to create a central chute holding the bolus.
Chute form.
Now the extrinsic directors take over. The anterior fibers of the genioglossus, working with the styloglossus, press the tip of the tongue firmly against the hard palate, right behind your front teeth.
The front exit is sealed. The food can only go backwards.
Exactly. Now the foundation activates. The jaw is clamped tightly shut by the powerful muscles of mastication. The mandible becomes a rigidly fixed anchor. With the jaw locked, cranial nerve V fires, and the massive mylohyoid hammock contracts violently.
The living ground lifts.
The entire floor of the mouth lifts superiorly. Simultaneously, the anterior belly of the digastric and the geniohyoid muscle contract, pulling the hyoid bone forwards and upwards.
Wow.
This massive elevation of the entire floor physically crushes the back of the tongue up against the roof of the mouth, acting like a hydraulic press, squeezing the bolus of food backwards towards the pharynx.
But as the food moves backwards into the throat, we face a critical evolutionary danger. The windpipe, the airway to the lungs, is right there. If the food drops in, we choke.
This is where the posterior guy wires fire to save your life. As the food enters the pharynx, the stylohyoid muscle and the posterior belly of the digastric, both commanded by the facial nerve, contract violently. They pull the hyoid bone superiorly and posteriorly, up and back.
The threading of the needle pays off.
Yes. This up and back motion of the hyoid bone mechanically forces the epiglottis to fold down over the larynx, tightly sealing your airway. Simultaneously, it physically widens the opening to the esophagus.
Airway sealed, esophagus open.
Finally, the styloglossus and hyoglossus muscles contract in unison, pulling the base of the tongue backwards and downwards like a heavy piston. This drives the bolus deep into the esophagus and physically blocks the throat, preventing any of the food from regurgitating back up into the mouth.
And all of that, the shape-shifting, the floor lifting, the pulley yanking, the airway sealing, the piston driving, all of it happens in a fraction of the second.
And every millisecond of that motion is monitored by the sensory fibers of trigeminal V3, orchestrated by the master motor commands of cranial nerve 12 and perfectly lubricated by the autonomic commands of cranial nerve the 7th. It is an absolute masterpiece of functional anatomy.
It truly is. Let's do a rapid-fire distillation of the key takeaways from Chapter 15 to cement these functional models before we finish. First, the boundaries and the foundation.
The submandibular region is the functional bridge between the head and the neck. The mylohyoid muscle forms the true, literal floor of the oral cavity. It is the hammock that elevates to initiate the swallow.
Second, the tongue.
The tongue is a muscular hydrostat without a skeleton. Its function is split into intrinsic muscles, which act as shapeshifters to alter form, and extrinsic muscles, which act as directors to move the entire structure through space.
Third, the complex wiring.
There is a strict division of labor. The hypoglossal nerve, cranial nerve 12, is the undisputed master of motor movement. The trigeminal's lingual nerve handles general touch and pain sensation. And the facial nerve's chorda tympani hitchhikes on the lingual nerve to deliver special taste and autonomic secretory commands for saliva.
And finally, the high stakes of the plumbing.
The rich vascular and lymphatic networks create both remarkable resilience through anastomosis and profound risk. The specific lymphatic drainage patterns, specifically the direct, early drainage of the posterior tongue to the deep jugulodigastric node, strictly dictate the grim prognosis and aggressive surgical intervention required for posterior lingual cancer.
As we wrap up this deep dive, I want to leave you, the listener, with a final thought to mull over. We've spent all this time breaking down the intense mechanical engineering of the floor of the mouth. We've mapped the hidden cranial nerves, the anatomical anomalies of the blood supply, and the embryological gill arches that determine whether a muscle belly answers to the fifth or the seventh nerve.
It's quite a bit to take in.
It is. But I want you to step back and consider how the absolute simplest, most mindless acts we perform daily, whispering a single word of comfort to a friend, or simply swallowing a sip of cold water on a hot summer day, rely entirely on this ancient, highly congested, wildly complex intersection of anatomy. We take it completely for granted, we don't even think about it. But every single syllable you speak, every meal you enjoy, is a physical marvel orchestrated by the living ground beneath your tongue. The next time you take a sip of water, don't just swallow. Stop. Feel that hammock lift. Feel that architecture in motion.
Beautifully said.
All right. To ensure this functional architecture is firmly cemented in your mental model, we are going to transition into our learning reinforcement quiz. I'll read out the single best answer questions, and our expert will break down the options and the functional reasoning behind the correct answer. Let's see how much you've retained from Chapter 15. SBA, Question 1. Which muscle forms the true structural floor of the oral cavity? A. Geniohyoid. B. Anterior belly of digastric. C. Mylohyoid. Or D. Hyoglossus.
The correct answer is C, the mylohyoid. As we visualize, the mylohyoid spans from the mylohyoid line on the inside of the mandible down to the median raphe and the hyoid bone, creating the broad, muscular hammock that forms the literal floor. The geniohyoid and anterior digastric are associated with the region. They sit on it or below it, but they do not form the floor itself. And the hyoglossus is an extrinsic tongue muscle pulling downwards.
Excellent. Moving on. SBA, Question 2. A patient presents to the clinic. When asked to protrude their tongue, the tongue deviates markedly to the right side. Which nerve is likely injured? A. Left hypoglossal nerve, 12. B. Right hypoglossal nerve, 12. C. Right lingual nerve, V3. Or D. Left glossopharyngeal nerve, IX.
The correct answer is B, the right hypoglossal nerve. Remember the rowboat analogy. Injury to the right hypoglossal nerve causes motor paralysis on the right side of the tongue. The right genioglossus is dead water. When asked to protrude, the intact, powerful left genioglossus muscle pushes forwards, forcing the entire tongue towards the weak, affected right side. It points directly at the lesion.
Perfect mechanical reasoning. SBA, Question 3. Which of the following specific structures is responsible for carrying special taste sensation from the anterior two-thirds of the tongue? A. Glossopharyngeal nerve. B. Lingual nerve directly. C. Chorda tympani. Or D. Hypoglossal nerve.
The correct answer is C, the chorda tympani. This tests the hitchhiking concept. The chorda tympani, a highly specialized branch of facial nerve 7, carries the taste fibers. It merely uses the structural, physical pathway of the lingual nerve to reach the tongue. The lingual nerve itself, derived from trigeminal V3, is strictly a general somatic sensory nerve. It only carries touch, pain, and temperature, not the special sense of taste.
The fiber optic cable inside the subway tunnel. Got it. SBA, Question 4. During the act of swallowing, the hyoid bone must be drawn superiorly and posteriorly to protect the airway. Which muscle primarily assists in this specific posterior retraction to prevent regurgitation? A. Geniohyoid. B. Stylohyoid. C. Mylohyoid. Or D. Sternohyoid.
The correct answer is B, the stylohyoid. The stylohyoid, working in tandem with the posterior belly of the digastric, pulls from its anchor on the skull base down to the hyoid bone. When they contract, they pull the hyoid bone up and back superiorly and posteriorly. This action is critical for folding the epiglottis over the airway. In contrast, muscles like the geniohyoid would pull the bone anteriorly forwards.
SBA, Question 5. The primary duct of the submandibular gland, Wharton's duct, opens into the oral cavity at which specific anatomical structure? A. Sublingual fold. B. Sublingual caruncle. C. Foramen cecum. Or D. Palatoglossal arch.
The correct answer is B, the sublingual caruncle. The submandibular duct emerges from the deep process of the gland, travels forwards between the muscles, and opens onto that small raised papilla called the sublingual caruncle, which sits just lateral to the base of the lingual frenulum under the front of the tongue. The sublingual fold, option A, is where the minor ducts of Rivinus from the sublingual gland open.
And the final question. SBA, Question 6. Early and aggressive metastasis to the deep cervical lymph nodes is most strongly associated with a squamous cell carcinoma located in which specific region of the tongue? A. Anterior tip, B. Ventrolateral surface, C. Posterior portion, or D. Dorsal midline.
The correct answer is C, the posterior portion. This is the crucial clinical lymphatic correlation. Malignancies located on the posterior or back portion of the tongue bypass the superficial nodes entirely. They metastasize very early directly to the deep cervical lymph nodes, specifically targeting the jugulo-digastric node. Because these deep nodes drain directly into the massive internal jugular vein, aggressive early systemic spread is a severe clinical reality for posterior lesions compared to the slower spread of anterior ones.
Fantastic breakdown. That wraps up our extensive deep dive into the living ground of the submandibular region. Here are the details of this episode.
Submandibular region and floor of mouth, the living foundation of speech and swallow. Byline. Beneath the tongue lies a dynamic floor where muscles lift, glands flow, and life's simplest acts quietly depend on intricate design. Episode description. If Chapter 14 was about hidden corridors, this chapter is about living ground. Because here, beneath the tongue, lies a region that. Because here, beneath the tongue, lies a region that moves. Because here, beneath the tongue, lies a region that secretes. Because here, beneath the tongue, lies a region that secretes. Because here, beneath the tongue, lies a region that. It is not static anatomy. Because here, beneath the tongue, lies a region that. It is functional architecture in motion, and everything converges here. And everything converges here. Air becomes speech, and everything converges here. Food becomes swallow, and everything converges here. Thought becomes articulation, and everything converges here. Key takeaways, and everything converges here. Submandibular region is a functional bridge between head and neck, and everything converges here. Pomalohyoid forms the true floor of the mouth, and everything converges here. Tongue intrinsic, shape, plus extrinsic movement, and everything converges here. Hypoglossal nerve controls nearly all tongue movement, and everything converges here. Salivary glands are essential for lubrication and digestion, and everything converges here. Rich vascular and lymphatic networks create both resilience and risk, and everything converges here.